So the Wittig reagent is going to allow us to transform a carbonyl into an alkene. And this is going to be an irreversible reaction. So if we want to look at the generic scheme, we can see that we have some carbonyl here. This could be an aldehyde or a ketone, and we're going to react it with our Wittig reagent. The Wittig reagent is going to have some R component here that is bonded to this triphenylphosphine, or PPH3. Again, and this is through a double bond. What's important to realize, though, is that this does have a resonance structure, and it's going to be the resonance structure is going to create what is known as an ylide. So for our ylide here, we're going to see that there is a positive charge on our phosphorus and a negative charge here. Because this is what are we doing with our resonance structure? We're pushing the electrons in this double bond onto our carbon here. So we end up with an ylide where we have these two adjacent charges. So this is going to be the ylide. So again, this is a resonance structure, right, of our Wittig reagent. So now getting this out of the way for a second, we can now see what we're generating as our product, which is going to be an alkene. So you'll see we have our R1 and our R2 still in place, and now double bonded, because we have an alkene, we can see that we have the R group from our Wittig reagent. Now, it's important to keep in mind is that if we wanted to look at the actual mechanism, there are a couple steps, but I guess sort of a basic idea of what it is we're doing is if we just want to generate some generic carbonyl here and react it with our Wittig reagent. For simplicity, let's just say we have, again, our PPH3 double bonded to some R group, let's say CH2. What's going to end up happening is we're really just replacing this oxygen here with the R group that's on our Wittig. So our product would look something like this. So this, keeping everything simple, is all we have to see being done with our Wittig reagent. Right? We just replace the oxygen here with the R group on the Wittig reagent, and that's our product. Now, let's take a closer look at the actual steps of this reaction. There are going to be two main steps, right? Or two main things we got to do. The first thing is actually generate our reagent, right? Generate our Wittig reagent. And to do that, we're going to need an alkyl halide and a strong base. Now the second thing is going to be actually reacting the carbonyl with our Wittig reagent. We'll just say WR for now. So let's start with the first thing, right? How do we generate this Wittig reagent? So as I said, we need to react our alkyl halide. So what are we reacting it with? Well, first we're going to have to react it with our triphenylphosphine. So what does that look like? Well, we're going to have our P bonded to 3 phenols, right? Triphenyl. There's a lone pair here. And this is going to react, like I said, with an alkyl halide. So we'll have an R and some X. Again, our halide here, some halogen. It could be chlorine or bromine. We'll see why that's important. And what we end up having here is an SN2 reaction. So we have the lone pairs on our phosphorus attack this carbon, which then actually kicks off our halogen here. Because look, halogens we know are good leaving groups, right? It's going to kick off that halogen here through an SN2 reaction, giving us something like this, PPH3. So what do we do now? Well, we have this PPH3 that also has a positive charge, by the way. And let's not forget that there are also invisible hydrogens on this carbon. So now it's at this point, right? It's the first step. It's at this point that we react this with a strong base. So if we have our hydrogen here, react it with some strong base. This could be, butyl lithium. This could be butyl lithium, which is, a very common base that we use with the Wittig reagent specifically. Or it could be, a sodium hydride, anything we want to use, just some very strong base. So as generically, we can just write some base. So we react this with a base that is going to deprotonate, push these electrons off to generate a double bond, giving us our Wittig. But like I said, once again, we can actually use these electrons, push them off here to generate that ylide, which is the resonance structure. So PPH3 with now a plus. We have this lone pair here. But anyway, this is how we're able to generate our Wittig reagent. Now, what about the actual reaction with the carbonyl, right? That was the second thing. Now that we have our Wittig, we can react it with the carbonyl. So when we're drawing this out, it tends to help to actually kind of flip this sideways a bit, as it allows us to, well, you'll see why. So we have this R, let's just call it R1, we have our PPH3, and there's a plus charge here, plus. This is a 3. Now, we react this, remember, with our carbonyl, right? So we can have the two R groups, and we can have an oxygen. So what's going to happen here is two things. We get this lone pair to go on, attack the carbon, while at the same time, we actually get these electrons to go and attack that positive charge here on our phosphorus. And why is this happening? Well, firstly, we can see that this is going to be a great nucleophile, right? The lone pair here, we have a negative charge, and so that's going to be highly nucleophilic. And if you remember anything about carbonyls, it should be that the carbon here is going to be a great electrophile. And that is because the oxygen is going to be drawing most of that electron density towards itself, because we know oxygens are highly electronegative. And so this carbon here is going to actually have a partial, it's going to have a partial positive, meaning it's a great electrophile. And then we can see that the oxygen here, like we said, is going to have greater electron density, so there's a partial negative, and we can see there's a positive there on our phosphorus, so we can then get another attack from this side. So what ends up happening then? Well, what ends up happening is we get some sort of box-like structure here. So what we see is we have that R group still bonded here to that phosphorus, the PPH3, and we now see a bond going to that carbon, which still has those two R groups, right? We have the R2, R3. Then we have this bond to that oxygen, which is a single bond. But if you remember, these electrons now go to the phosphorus. So we get something, this is the bond between the phosphorus to the oxygen, something like this, kind of looking like a box. So now this ring structure here is actually known as an oxophosphatine. And so an oxophosphatine is we have two carbons, one phosphorus, and one oxygen. So this heterocyclic sort of structure, this ring here, this four-membered ring, is going to be very short-lived. And that's because we know that four-membered rings are not very energetically stable or favorable. And so we have some sort of spontaneous decomposition of this. And how does that happen? Well, we have these electrons here collapsing towards the phosphorus-oxygen bond, and then we have the electrons going here towards this carbon-carbon bond. And what this is going to do is it's going to decompose this ring, right, generating two sets of double bonds. Really, one of them is going to be involved in our alkene, right? This carbon-carbon double bond. We have R1. Sorry, excuse me. This is supposed to be our R1. So then we have the R2 and R3, which were a part of our carbonyl. And we're also going to get, I'll just draw it up here, we're also going to get our PPH3 double bonded to an oxygen. And that byproduct there is what's called a triphenylphosphine oxide. All right, now having this in mind, if you want to take a quick look at a problem that you may encounter on an exam and see if you're able to approach it based on what we've learned so far in this video. Let's say we have a structure that looks something like this, which we're going to react with a couple things, right? We're going to react it with these three different compounds here. So what is it that we are going to get? So the first thing that may be confusing is, hey, how is this a Wittig problem, right? Well, what we're actually noticing, or what you should notice here, is that this encompasses both the generation as of our Wittig reagent as well as the actual reaction with the carbonyl. So if you notice, this is that alkyl halide that we talked about. We'd see a halogen along with an R group. So this is that RX that we then, remember, react in two steps. Firstly, we react it through an SN2 with our triphenylphosphine, and then react with a strong base. Remember, so we said we could use butyl lithium, sodium hydride. So this is going to work as well. Sodium hydride here is going to be that strong base. So these first two steps are going to allow us to generate the Wittig. And it's the second, or rather this third, that is the actual reaction to generate then the alkene. So without going too deep into the actual mechanism, let's see what it is that we generate. Well, through the reactions with the first two reagents, we're able to generate our ylide, right? We're able to generate our reagent. So what is that going to look like? Well, if you remember, it's going to look something like this, where we have that benzene, right? We still have that benzene here, but then what we're going to have is that double bond here to our PPH3. So again, this was very similar to what we saw before, where in this case, this is our R group. If you'll remember, through the SN2, we'll actually lose the chlorine as the leaving group, so there won't be a chlorine in our actual Wittig reagent. So if this is our Wittig reagent, which again, if you want, we can redraw in its resonance form, where we end up with something like this, right? The lone pair, negative charge, PPH3, and a positive there. So what we're going to then do is we're going to react this Wittig with our carbonyl, which is that third step here. So if we're reacting with our carbonyl, what do we get? Well, if you remember generically what we talked about is if you have a carbonyl and we react with a Wittig, if you remember before, all we do is we replace the oxygen with the R group. So here, this is our R group. So what is our product going to look like? Well, it'll look a little like this. There's our double bond, and then the two R's that make up the carbonyl. So this is going to be our product here. This is going to be the product. So feel free to now on your own try to draw out the actual mechanism with all the arrow pushing and all that good stuff on your own based on what we saw earlier in the video, hoping that shouldn't be too difficult. So this is going to be our product for this reaction here. Alright, so that brings us to the end of this video. If it was helpful, please show your support by liking and subscribing. Leave in the comments any questions you may have as well as suggestions for future videos, and I'll see you in the next one.